We'll start off for a quick second looking at...
This is IBM research, and we're supposed to be pushing the limits of science. I mean, that's our job, to look for exploratory challenges that help us drive science.
There's two types of innovation. There's incremental innovation, improving existing products and advancing them in sort of a linear fashion. But we like to present our teams, and our teams even generate for themselves, grand challenges.
So what makes a grand challenge is, first of all, it has to be difficult, right? It has to be a challenge. It has to be inspiring.
Chess was a grand challenge that was identified in the 60s. People said that no computer will ever beat a human chess grandmaster.
It would be a landmark to show that we understood computer technology well enough to take on this task that we thought was really restricted to human intelligence. And we did it with Deep Blue.
Another grand challenge is around using computers to map the human genome. We call the computer Blue Gene, Blue for IBM, Gene for genomics. We encourage people to work across disciplines on these grand challenges. And it's these sorts of things that produce the big breakthroughs that IBM has done for the past 100 years.
Language is an area where, from the very beginning of the computer era, people kept expecting computers to do reasonably well at it. They expected computers could talk, and they could understand what it is you're asking for, and then they can do that thing, or they can answer that thing. And so far, the computers have failed to deliver on this promise.
There's something called open question answering that has been a problem in computer science from the beginning. It's much more difficult than search. It's not about a single keyword. It's much more the way normal humans communicate.
Humans communicate very fluently in images, in literature, in writing. People get natural language because it's a human artifact. They relate those words and those phrases and those ideas back to the way they think. They ground that information in human cognition, their human experience. But that's not written in a formal database language or a formal mathematical language that computers can understand.
Computers are used to unambiguous things. Human language, completely the opposite. Last night, I shot an elephant in my pajamas. How it got in my pajamas, I'll never know. We know what the pajamas are modifying, but the computer, it's just as likely that the elephant's wearing pajamas.
And that's where computers struggle dramatically, and that's where we want to make them better. IBM executives were really interested in doing sort of the next big grand challenge, the next Deep Blue.
Do you have any questions before we begin? Everything's going to work pretty much exactly the same way it did for you on the show. The only difference is we do not have a time limit, so we will play.
I had heard some rumblings about maybe we would take a look at doing question answering on a big scale. Maybe we would look at doing something that could take on a real challenge, like Jeopardy.
Deep search and deep analytics was becoming a tougher and tougher problem for general purpose computers. So we said, well, let's build a specialized computer to do this and do it at an incredibly fast rate.
Let's take a look at our categories. Philosophic ideas, Bergopolis.
Ultimately, we're not playing Jeopardy. What we're trying to do is make computers better at processing all that natural language content. Can you imagine computers communicating more fluently in natural language?
In 1778, this man, the Elder, suffered a fatal collapse minutes after speaking against colonial independence. Watson.
Who is William Pitt?
That is correct. Watson wins the game.
It is irresistible to pursue this, because as we pursue understanding natural language, we pursue the heart of what we think of when we think of human intelligence.
Welcome. So today, I'm actually going to give you guys a brief overview of Watson and the problems that we faced as we were really focusing on the whole problem of natural language processing, some AI, and also looking at how one can answer open domain questions. In other words, any question. The Jeopardy experience for us was one of proving the technology. Could we actually do it? Could we actually get questions in and then answer them? And by the way, answer them across about 2,500 domains. So the presentation really is going to talk to that. So first things first. Let's talk about why is Watson important. And it's important not only to IBM, but clearly important to the whole industry. Because as you all know today, most folks actually have questions. They distill them to a bunch of keywords. We then basically use a search engine. We get back a whole bunch of documents. And then the next thing that actually happens is we search the documents. And depending on how deep the question is, we'll go back and go through the whole process again. When we actually started the Watson project, it was really all about, I want to ask a natural language question. I want the machine to actually figure out what that question was, looking at exactly the sentence and the sentence structure. And then what I wanted to do was produce possible answers internally in the machine, work through basically whatever evidence we might have, and then actually respond with the appropriate answer. As John Kelly actually said, who's the what is John Kelly? He is the Senior VP from Research. We do a grand challenge about every 10 years. And one in natural language processing in AI was made possible because of the number of changes that actually happened, not only in NLP, but also in terms of storage, processors, and looking at actually shared networks. So with all that said, you know, let's just look at human language. And we'll talk English just for right now. English at best is ambiguous, very context dependent. A lot of things are very implicit in the language. And when I look at you, you actually, in some cases, actually have to see me to actually see if I'm laughing, because I might actually be, had a pun in the middle. And as you saw in the video, there was actually a piece on the elephant and the pajamas. Wonderful English sentence, but I got to tell you, the machine would have gotten that wrong up until a few years ago. So let's think about a few things. Given a bunch of questions that we might have, and by the way, this is outside of the Jeopardy domain. I mean, not as a game show now, just in general. Whether it be in medicine, whether it be in finance, whether it be in e-government, it doesn't really matter. Let's look at basically the natural language processing, look at the domain that we're going to have to answer the questions, and then let's see how we're going to be able to do it. So here's an easy one. Does anyone in the audience know the answer? 0 or 1. Okay. You can't even comment. Yeah, shot. Okay, so we've got the answer. Next, okay, what do computers do very well? We actually know how to write in COBOL, and we actually know how to actually look things up in a database or a data structure. Okay, we also know how to do extremely well look at structured information, and we know how to structure information. We've been doing this for the better part of the last 30 to 40 years. But you know, we also in a computer can actually figure out very easily that David Jones is actually equal to David Jones. However, one of the things we actually can't figure out is if Dave Jones actually is equal to David Jones. And that's a key piece, by the way. So when we actually look at hard problems, okay, here's an example, very structured, okay? Where's Einstein's birthplace? Okay, well, let's actually change that and say, one day from among his views of Ulm, Otto chose a watercolor to send to Albert Einstein as a remembrances of Einstein's birthplace. That is a good sentence in a lot of ways. One, from a computer side and looking at the natural language, is birthplace equal to where someone's born? Forgetting just looking at the sentence itself. Next thing you got to think about is, does auto really matter? How are we basically going to start breaking up the sentence? I'll give you another example. And by the way, these are the actual problems that you're going to face when you start looking at building systems like this. This has to do with General Electric and Jack Welch. If leadership is an art, then surely Jack Welch has proved himself as a master painter during his tenure at GE. Very complex English sentence to look at. So why did we actually do Jeopardy? Because Jeopardy actually forced us to start looking at natural language processing and start really looking at evidence, deep evidence, and then actually start looking at how sentences actually can fit together and how actually subject and verbs fit together with predicates. So with all that said, you know, can anyone in the audience answer this question? This fish was thought to be extinct millions of years ago until one was found in South Africa in 1938. System has to parse it, okay? A category is ends in TH. I'll give you an easy answer, coelacanth, okay? And then if you look at the next question, the answer is light, and then the next question, it'll be his resignation. As you look at all of these, okay, the real problem that you're really looking at addressing is, how do I actually break the sentence apart into subject, verb, object pairs, and then how do you build the graph? Then once you build the graph, how do those graphs fit in with all the other millions of graphs you have in the system? Because you're going to really need that when you look at open domains. Now, probably someone in the audience could easily have said, well, why don't you guys think of this as a database project? Use a little NLP, and then basically you could start storing things in databases and just look them up. The problem is you've got the long tail effect. In the case of Jeopardy alone, there are 2,500 categories. And in the case of real life, there are a lot more than that. So we clearly knew we couldn't attempt to build any kind of database. And we couldn't even try to build any model of the world to do this. Really what our focus was, reusable natural language. Now, when you look at all of these things, the machine really has to start thinking about doing a lot of things before you can even answer Jeopardy. Go look at medicine or any other of the vertical possibilities. You really need to start thinking about how all these sentences fit together in the subject, verb, objects. Okay, examples, inventors, patent inventions. While everyone in the audience who knows English well knows that's possible, this is really very hard for a machine. Okay? And then you can look, is a fluid a liquid or is a liquid a fluid? We're going to come back to that one in a second. But I want you to think about the following. In this sentence, in cell division, mitosis splits the nucleus and cytokinesis splits the liquid cushioning the nucleus. Okay, if there's any biologists or chemists, we already know the answer's going to end up being cytoplasm. But the reality here, okay, is you actually have to start figuring out, of the candidate answers of organelle, vacuole, cytoplasm, etc., what is a liquid, what is a fluid, okay? Now, if you look at it just straight out, okay, cytoplasm is a fluid. Now, first question you got to ask yourself, is a fluid a liquid? And by the way, depends on if you're a physicist, you know it's not. Liquids are fluids, however. Okay, now, if we go out to a taxonomy like WordNet, which we had in Watson, basically we'd find out that the answer is no. However, what we actually needed to do in Watson is actually learn that people actually consider fluids liquids and liquids fluids. And we do this after many, many iterations of looking at sentences and ingesting material. Going a little further, okay? Here's a case of a sentence where, as everyone in the audience has done, I'm sure, many, many, many times, they look for keywords. And they do just look at keywords and see, these two things are actually a match. So in this sentence, it says, in May 1898, Portugal celebrated the 400th anniversary of this explorer's arrival in India. Okay? Let's look at the other part. In May, Gary arrived in India after he celebrated his anniversary in Portugal. If we just do a keyword match at the end of all this, we're going to think that Gary actually is the explorer. Okay, because that's really how keyword matching is going to give the evidence. However, we really can't do that. We actually have to look for much stronger evidence when looking at sentences. So let's look at another one, okay? And in this case, on the 27th of May, 1498, Vasco da Gama landed in Caput Beach. Lots of things happening on this one. First things first. Okay, landed in, does that equal to arrived in? Again, we're back to natural language processing. We're back to figuring out how things fit together and how people use things. The answer is yes. Okay, is Caput Beach, for example, in India? The answer is yes. We got that looking it up through geospatial reasoning. And then you have the temporal reasoning, just looking at dates. Okay, 1498, 400th anniversary of the year is 1898. So, as the researchers actually looked at creating systems to do this, they actually had a bunch of different variations. In 2006, they actually had a system called PCANT. It was another NLP system that did question and answer open domain. And it pretty much was lower than the graph you see here. But that graph actually is the beginning of Watson, okay, with just a standard stack we were using at the time. If you looked at the Jeopardy case on top, every single one of those dots is a Jeopardy winner. And the red dots actually are the grand champions. And if we really wanted to play in against grand champions, we had to hit around the 90th percent answered, and by the way, we had to be about 90 to 95% correct. So, with all that answered, you know, in your mind, we had to make a very huge leap. And that huge leap actually brought us to this architecture, which we're going to talk a lot about in the next few minutes. The architecture actually begins by decomposing the question. And then what we're going to do after decomposing the question is we're going to look this up via what we're going to call a primary search. And our primary search is actually using two engines. One of them is called Indri, and the other one is called Lucene, both open source. So we're going to look that up. And the next thing that happens is out of those searches, we're going to actually determine and start hypothesizing what the answers are, which then brings us into the next part of the pipeline where we actually start looking at evidence. And evidence actually is, can I find anything about that specific question? And then after I find it, I can start scoring these. Again, I need to figure out what kind of confidence I actually have in, you know, how I'm looking at things. Then after I do the evidence, I can actually go do much deeper evidence by looking much deeper in corpus, or corpora, actually. Next stop after that is I want to bring all this together. The bringing all this together happens in the synthesis side, and at this point, if we stopped, we would never get near the winner's circle. Why? Because our confidences aren't not yet up in the 90s. They're probably in the 70s, or less actually. And the only way we actually could bring them up is actually use machine learning. And in machine learning, the idea is you actually give the machine questions that are correct. Okay, your test questions. You actually create a logistic regression, and then you actually run things through that regression. And that's actually how we ended up with the final answers. Now, with all that said, I'll give you another couple of good points. In this case, we can actually look at Chile shares its longest land border with what country? Okay, clearly the answer is Argentina. However, if I actually just went and looked at how many times Argentina would appear with another country, you'll actually find that Bolivia was actually going to be found. And we actually have to look much deeper at the evidence. Okay, in this question, this is actually a much more interesting question for so many different reasons. Okay, you'll find Bethel College and Seminary in this holy Minnesota city. Few things. First things is catch the pun with holy. Really a key part of the sentence. The other side is you need to know it's in Minnesota. Okay, so you're going to have to make two checks right there. Okay, and then if you actually had something, you'd actually be able to figure out where Bethel College is. But when you start looking at supporting, okay, we found St. Paul from passages, okay, and you look at the popularity of answers as you go down all the way through, you're actually going to end up at a point where you think maybe the answer is actually South Bend. Okay, but the reality is once you start looking at the pun, okay, being holy, holy is saint, and that would have given it away. Okay, moving on. This is actually the graphs from how we actually built Watson up. Okay, and we're going to start on this one with times. So the architecture I actually showed you, this was the baseline at the beginning of 2007. Then we jumped to 12/2007, and every single one of those other jumps, as you noticed, they got pretty small, had to do with some very small incremental change we made in the system. Might have been better logistic regression algorithm, but most of them actually had to do with better support retrieval of information, okay, and looking through. Now, later on today, I'm actually going to do a demonstration, and I'll actually show you on a test machine what Watson can do. Or I should say, more importantly, not what Watson can do, but what the actual framework called Deep QA can do under the covers. And this is actually Deep QA. And one of the things we'll do is actually looking at how everything gets split up. So given that, you can easily see from one question, I'm actually going to look at hundreds of sources of information from one question. I'll end up with hundreds of answers. From the hundreds of answers, I'll go look at thousands, if not 10,000s of pieces of evidence. And then really when I start looking at the scores, I got to deal with hundreds of thousands of numbers. Now, one of the things about the architecture that really drives you is you actually have to do all of these things in parallel. So one of the things that we actually had to start thinking about was parallel architectures that would have been, number one, asynchronous, and then we could just scale this out. One of the things that we did was look at how long it would take to answer a question on the average PC. One question. Okay, given enough memory, it actually was taking about 2 hours for one question. Playing Jeopardy, by the way, we had to answer questions in less than 2.6 seconds. Now, answering the question is one thing, but we actually had to have the confidence to answer the question. And that actually is the key here, because confidence is actually driven by actually scouring basically your sources. And in the case of Jeopardy, we actually had about 2,880 cores. And we went out and used every single one of them depending on the question. So if you look at this machine, okay, that machine right there that played Jeopardy, okay, with all of that processing power, actually only did one thing, answered one question. That's it. Now, we got pretty busy at various times, clearly. Now, besides basically having the processors, one of the other things we had was we actually had a guaranteed performance. We actually had 16 terabytes of main memory that we shared. And we loaded it, by the way, with everything. And then we compacted it because we actually ran out of memory. So when you start looking at this, you say to yourself, well, where is this really going? What was under the covers and things like that? So looking deeper under the covers, and we're actually going to go much deeper in a second, you really look at there's various types of analytics running. Okay, there's stuff that we wrote that's internal, purely internal to the deep QA architecture. But if actually we got clean data in, it's much easier to find answers. Okay, so if you actually run some analytics against something, it's much easier for us to work with. Did we get a lot of that? No. Now, what I'm going to do is actually jump to a different presentation that actually brings us into a much deeper spot. So, I think that at this point you need to think about a few things. The first of them is, does Watson think? Okay, this is not an AI discussion. Watson doesn't think. Watson actually does some reasoning. And there's a huge difference between the two. Okay? All it is, it actually can reason looking at things that we put in there and relationships that we put in there and figuring out confidence, the answer to a question. Okay, that's given in natural language processing. Whether it's structured or unstructured, it really doesn't matter to Watson. And basically, we will combine many, many different things to give us optimal ends. When we actually analyze a question, okay, one of the key things that you're going to start looking at is forward and backward chaining. Because when you walk out of the Jeopardy case and you go into medicine, we're going to actually have to restart basically the whole pipeline again and again and again, because we're going to find out more information, whether it's initially with the patient's symptoms, or it's basically the patient's long-term history, or it's lab tests, or it's drugs, because each and every one of these things will restart you because you actually have more information. So we have to do forward and backward chaining, and then that actually is going to help us get to higher levels of scoring. The other thing that you got to think about in Watson is everything was about heterogeneous information. We had nothing rather homogeneous in this case. Okay, everything was from all different types of sources, which will be coming up in a few more charts. But we actually had to focus in on many, many, many different possibilities. Clearly, it doesn't think. Okay? One of the key things which is in English is full of nuances, metaphors, puns, and it's also full of relationships that come off of many, many different objects that sometimes mean nothing. You can just throw them away and you still have the same meaning of the sentence. So when you start thinking about how that's going to work in an open-ended system, you really get to a point where context is everything. And how you're going to figure out the context? You start by looking at the grammars. And you break down basically what's come in. Then you start looking for all of those subject-verb-object pairs. And then you start looking at evidence based on all of that. And then you actually move forward. Or you actually have to resign yourself that you have some contradictory information. One of the things which people always think about is Watson thinks, Watson reasons. What does that really mean? Well, it's a machine. This machine actually runs Linux. Okay, many versions of, many copies of Linux, but it runs Linux. When you start looking at the team that actually created Watson, there were 25 people that worked for 4 years. But then you have to think of the 25 years that they worked before on natural language processing and AI. So if you look at that team, okay, the duration of their project was about 4 years. More interesting than that was they wrote 1 million lines of code. Of the 1 million lines of code, you actually start looking at Java code and you look at Prolog code. Why Prolog? Prolog is a great language from 20, 30 years ago. It's all about relationships. Okay? Then you actually think about other things. Well, we actually had to talk to an interface. That interface was JavaScript. So as you look at the whole system, okay, you can actually look at it from the standpoint of concept, birth, and then rebirth. So it actually started in 2004 when a colleague of mine, Charles Lickel, actually gave the team a challenge. And as you heard, you know, earlier when I said Ferrucci, actually, who was the principal investigator, actually had a PCANT system, which was an answer, a question-answer system. And that actually didn't have the accuracy or the confidence or anything else, and that concept built up over time to where you saw them actually win at Jeopardy. The session later today actually talks about the road back. The road back actually is not game shows. It is actually going to be looking at other domains. Those other domains are medicine. The other domains are finance, legal, government, whatever you guys want to do, whatever vertical is interesting. Actually, you can use a Watson on. But you actually have to be really focused on what problem you're trying to solve, because it's going to take you an awful lot to solve that problem. You have to ingest a ton of information, okay? And you're going to have to put in a lot of time to figuring out how to train it Watson up. If you want to go through those steps, you're clearly going to end up in a machine that's going to be able to reason right and wrong. Now, in the presentation, which is going to be made available to you, you'll actually have lots of pointers to old things. When Ferrucci's team actually was doing the PCANT work, one of the things that they actually looked at doing was creating the unstructured information management architecture called UEMA. It's actually out in Apache. And if you look at what UEMA does, it enables applications to get decomposed into components. And if you look at those actual components, they actually can be made up of, which hopefully this will be the next chart, which it isn't, but that's okay, things that work on your NLP that is inbound, okay? When you look at this chart, you got to say to yourself, well, where are the key pieces of the system? Where is, if you want to call it, the glue, okay? So the front end here, as I said, was primarily came from Indri and Lucene, okay, open source code, okay. Underneath this, there's actually a whole other part of the system, because this is the runtime view. Okay, there's the ingestion view, because the machine actually has to ingest lots of material. In the case of Jeopardy, it was 20 terabytes of information, okay. And the material you start looking at in the other phase is really going to look at how do I ingest it, and as I'm ingesting it, I have to create all of those maps, so that I'm going to use them in the scoring side of this. And then the model's clearly at the back end of this. Now, back to ingestion here. In ingestion, you basically read material in, okay, and that material that's going to be read in, some of it is actually going to be used to give test results on test sets, okay. The test sets are, you know, we actually have in our system these days, one test set that takes 55 hours, another one takes about 11 hours, so on and so forth. None of these are short. And the idea is that we test it with the same, we actually change the system and test it to see if we're getting more accurate and can build up our confidence. And that's really what this whole loop is about, because once I actually ingest the information, I actually have the ID that's necessary for me to find it, and then later on I'll actually use it. Now, beyond that, let's talk now about what was under the covers. What was ingested with Jeopardy? Okay, and this is an important point. This was ingested with Jeopardy. This is not going to be with a commercial offering. Wikipedia, actually, all the wikis, okay, was actually ingested. Wikipedia actually can answer about 80% of the questions. However, you'd have no support evidence saying that those answers are actually that you're confident in the answers. Next thing is you start looking at all the others, they actually added the ability for us to find relationships. As I said earlier with WordNet, okay, WordNet is a taxonomy. It actually lets me look at, you know, the meanings of words and how words fit together. We also actually had the New York Times, the digital version of the New York Times, Encyclopedia Britannica, World Book, you name it, we actually had it. We also were extremely lucky in that, in the case of Jeopardy, the fans actually created a site with every possible question and every possible answer. And those answers and questions became our test suite for Watson. So that actually gave us the point where we went up and started playing human beings. Now, when you look at ingestion, you have to start thinking of the inbound question, what domain it actually fits in. Then after you look at the domain, you actually have to start thinking about, well, if it fits, let's say, in countries, world countries, okay? You're going to have to stick it in the right place. You're going to have to make sure, basically, there are enough all your pointers are correct so that you can actually find it at a later date, so that actually you can use it during scoring and also during final analysis. And then you basically have to start thinking about, well, how am I going to ingest information and actually ingest it in a relatively fast time? Okay, remember, we're talking 20 terabytes. By the way, 2 people of those 25 team actually were human annotators. They actually went in and annotated code because the code actually had no metadata associated with it. Okay, no clue. It actually helped us actually figure out what some of the things were. Albeit Jeopardy didn't need the metadata, but it made life easier. We actually could figure out how to start looking at it. And we actually went a bunch of other steps. If you look at the play architecture of the machine, it really is very simple. Okay? Ingestion in, break it apart, go out and do the searches, go do basically your generation of your hypothesis, go out and do a very lightweight evidence search, and then actually do a much deeper one. And in each of these, by the way, we're getting indexes of confidence. And then at the end, you basically go out and do run against logistic regression algorithms. Now, we can skip UEMA, okay? A bunch of different things. Watson actually, because of UEMA, we actually can put code that actually runs, okay, in it called annotators. And annotators, in our case, we have actually about 150 right now. They could be everything from a basic, you know, give me co-reference, give me a lookup, okay, to actually finding out, you know, different ways of looking at information of, let's say, men get certain diseases, women get certain diseases. This would all be done in annotators. But you wouldn't talk about the diseases. You just say men and women and what makes sense, okay, for these. And then you start looking at your geospatial, your temporal reasoning, and all the other parts as you start marching through this. Now, let's just skip a bit on here and start thinking about question analysis. In question analysis, the first thing you need to do is figure out the grammar. You split it apart. Happened to be that the Watson guys actually had a wonderful guy who wrote a slot grammar parser. Okay? And first thing is we actually ran through that. Okay? We found out the focus of the question. Then after we found out the focus of the question, we actually looked at the lexical answer type that we'd be going for. Okay, and then classify everything and select everything. Then we actually use those search engines I talked about before. Now, one of the things as I start looking at scoring, okay, we had over 50 techniques right now to score because it depends on what we're looking for. It depends on those relationships. Okay, so we actually have a whole bunch of information that we've actually collected, and what we need to do is ensure that no matter how we start processing this, we actually use the same exact process because clearly we can't have alternatives at the end. Now, in final merging, we on 345? Okay. In final merging, okay, it's really looking at bringing all those pieces together and then dropping them through the model. Okay, now, in the case of Jeopardy, okay, that actually was something we created because in that game you actually have to, the machine actually had to push the button. Now, I want you to think about something. The machine only would push the button when it was, I think it was over 70% confident it had the right answer. Okay? And remember, it actually had to do this in 2.6 seconds or less because it knows that someone else would buzz in. The other thing is the avatar that actually talked. Well, virtually talked. Okay, it was actually created by some guys at Automata Studios. Okay, so these are the background of you know what went on. We already talked about this. The only piece that we didn't talk about was looking at how we actually started storing that information. I told you that in the case of Jeopardy, we actually went forth and put it all in main memory. Well, before it was on memory, it was actually on a NAS disk that every processor actually had access to. And in this case, their NAS happened to be 20 terabytes. So up to this point, I've pretty much given you an overview of Jeopardy up till February of last year. From that point forward, it actually came into my hands. And that's actually where you have to start thinking about how do you move from a machine that's in the tens of millions of dollars to one that is a lot less than $1 million. Okay? Maybe even $500,000. Another way of putting it is, how do I move from 2,880 cores to something like 200? So lots of different problems. How do I move from a machine that had no security, by the way? Watson machine that when it played Jeopardy was not attached to any network. How do I move to actually add security to the machine? Then more importantly, depending on who you are, is the next step. How do I start thinking about how human beings are going to start looking at the machine and getting information in, and how can they get information out? Now, one of the things I didn't talk too deeply about was this whole thing about machine learning. Machine learning is all about models. It's all about, you know, you can increase something, for example, focus your confidence in on material that came from my installation. Think about a government. I only trust my information, even though I like information coming from other sources, weigh mine more. Or, in some cases, you may want to weigh other things. So you really have to think about, in the case of the machine the way it is it's baked in. So we're going to actually have to start allowing people to play with this. The other side of it is, since there is so much source code here, open source code here, you have to think about how, number one, the source code is actually being used. Did it make sense to use that source code? Because we're not in the research world anymore. We're actually going to try to make a product that actually will sell to many, many people. And then last but not least thing you have to start thinking about is, how am I going to look at information stored on the machine? Now, when I say that, I mean it in a bunch of different ways. Legally, copyright comes in at this point. I may have, for example, Wikipedia, okay, which I'll get into one second. I'll talk about that. Wikipedia actually is a very liberal license, but you know, anything that is combined with Wikipedia has to go back to Wikipedia. Not many customers, let's say, if we had a case of, let's say, legal LexisNexis database, I doubt LexisNexis wants to send it away, since they make so much money off of that. So we actually have to look at it. The same thing goes for Encyclopedia Britannica, you know, any newspaper that happens to be online. You needed to start thinking of breaking things apart. So where we are right now is about 2.5 months from delivering something commercially. And when I say delivering something commercially, that is, it will work on a machine that is 7 nodes is the minimum. So I've gone down from 90 to 7. Of those 7, I'll only have 8 cores per, so it'll be 56. And then the next piece of this, I also have to go from 16 terabytes down to 128 gig. That right there actually caused me more problems than anything else. Because how do you start going from a machine that was designed for pure storage and use storage to one that basically has to start going out to disk? Clearly we can do it. That wasn't the problem. We did it. But your performance starts to look pretty nasty. So all in all, you say to yourself, well, I went from 2.6 seconds on that huge complex, and you'll see us at about 20 seconds right now. Okay? Now, where's Watson going? Or where's DeepQA as an architecture going? First thing you need to think about is, from the perspective of where IBM thinks we can take the machine, it's to a great number of verticals. Okay? The first one that we're focusing on is healthcare. And actually, in the next session, I'll talk a little bit about why healthcare. But all you need to think about is this. Many, many diagnoses, almost close to 20% of diagnosis of critically ill patients are incorrect. Yeah, they get corrected along the cycle, but they're incorrect at day one. And by the way, of that, and just in the US numbers, almost 100,000 people die a year because of incorrect diagnosis or incorrect drugs given. Huge. Second thing is that, we believe we can actually build a system, and are pretty much going down this path, that actually can help a provider actually come up with a differential diagnosis, and then actually get to the next step, which is work on the final diagnosis with the provider. However, I want to come back to a point that I made earlier. This is not AI. This is not Hal in 2001 where he thinks. The machine is a machine. All it's going to do is give the information that we reasoned that would be correct out. And that reasoned information really comes to how we looked at those subject, verb, predicate, and objects. It all comes back to that one simple point. So with all that said, I can actually say, well, in the next session you'll see a little bit about Watson. We'll actually test it. I'll run 5 test questions. Let me tell you why they're my 5 test questions. Because I know chances are I can't find any questions you guys want to give. Now let's look at why. We're going to be running on my test cluster. Okay? My test cluster has one thing only in it, and it's Wikipedia. And you might say, well, Wikipedia will give us some answers that are correct. But the problem is Wikipedia actually does not give very much confidence because I only have one source. Okay? So I picked the questions. If you want to try to come up later, we can try other questions. But I picked 5 that I know absolutely will work. Sometimes. When you look at where we're going with healthcare, it ends up in a very different space. Or where we're doing with legal, it's very different. Because I'm only actually shipping Wikipedia with the machine only for one reason. So that you as a customer actually can ensure that the basic machine actually works the way I actually meant it to, at the level of precision and accuracy. And that's key, because the architecture I showed you is all about, it's a probabilistic. In other words, it's probably going to give you the same answer almost every single time. But if you bring in more information that actually changes that, it's going to change actually the endpoint. And this is one of the most interesting problems. You think problems as well as, a very big plus. Because the more information I ingest, the better the answers are going to be on the outside. However, as I said yesterday, I was in front of some computer science folks. Think about this one. This is the one I actually use as my test case. About 20 years ago, or a little less, a doctor in England actually decided that he was going to have a study that will prove that DPT vaccines cause autism. Clearly, a great number of the people in this room that are over 40 had one and didn't even think twice about it. What that caused was a huge change in medicine. The parents actually started saying, I'm not giving my kid this vaccine. Now, up to that point, let's just say Watson was running them. DPT was the obvious. It was wonderful. Everyone said great things about it. We were no longer getting tetanus or diphtheria or pertussis. All of a sudden, you end up with this flag, by the way. So this one report. Okay? Now, let's look at this. It depends on how you weigh the evidence, whether you're going to even see that report actually ever come out. And then not only how you weigh the evidence, but you find out, and this is where the human being has to think about it, is that was actually 6 patients were used and published. The study was bogus, by the way. But it was only bogus and proved 17 years later, or 16 years later. It actually had to go through 16 years of many, many people. And I want you to think of how many articles are actually there to say that DPT actually causes autism. And by the way, there were many parents that didn't give their kids the vaccine that ended up with some problems. And it was all because of this one report. And that report, depending on how it got into the system, might rise to the top or stay at the bottom. But in any case, with all of those gyrations, you'd have to report it. That's your problem when you look at a probabilistic system. Where are you on the clock? Are you at year 1, or are you at year 13 or 15 when there have been so many studies that say, no, that's wrong? And that's, you know, that's where we are. So one last thing on medicine. When you think of oncology, every single institution in the world actually has their own protocols. There are protocols that the world has in general for diseases. There are some for the institution, and then there are for the doctors. Question you got to ask yourself, forget about that we all might get sick one day. Which one ends up with more weight? The answer is it depends. So on that, I'll leave you until a bit later. Thank you.
Thank you very much. Give me algorithm to prepare my paper. It's not the same prepared.
What's the paper on? The first question is, we would say we need more information.
Could they do some dialogue with you?
Yes. So the Watson that you saw that played the game, no. The Watson that we're working on right now, the answer is yes. What's going to happen is we've created these advisors, and I think maybe I'll talk about them a little later, but the advisors actually are all about the interface, the user interface, and they actually call out to other pieces of code that are outside Watson. For example, if someone actually orders a CT or an MR with contrast, the first question that the doctor should think about is the person allergic to the contrast? That question will come back automatically before anything else processing would happen. So the answer is we've done this outside of Watson because Watson is only that one architecture.
Thank you, David.